In this video, we're going to talk about regular languages, which are used to specify the lexical structure of programming languages. To briefly review, the lexical structure of a programming language is a set of token classes, and each one of the token classes consists of some set of strings. Now, we need a way to specify which set of strings belongs to each token class, and the usual tool for doing that is to use regular languages. So in this video, we're going to present regular languages and define what they are, and then in subsequent videos, we're going to look at some examples of using them in actual programming languages. To define the regular languages, we generally use something called regular expressions. And each regular expression denotes a set. There are two basic regular expressions. If I write the single character C, that's an expression, and what it denotes is a language containing one string, which is the single character C. Okay? That's one basic form. So for any single character, I get a language with a one-string language with and then the only string is that character. Another basic building block of regular languages is the regular expression epsilon, which is the language that contains, again, just a single string, this time the empty string. And one thing that's important to keep in mind is that epsilon is not the empty language. Okay, so this does not correspond to the empty string, the empty set of strings. It is a language that has a single string, namely the empty string. Besides the two base regular expressions, there are three compound regular expressions, and we'll just go through them here in order. The first is A plus B, which corresponds to the union of the languages A and B. So this would be the set A such that A is in the language of big A, little a is in the language of big A, union little b such that B is in the language of little b. So just the union of the two sets of strings. Concatenation is like string concatenation. So if I have two languages A and B, or two regular expressions A and B, then the concatenation of A and B is equal to all the strings little a concatenated with little b, where A is drawn from the language big A and little b is drawn from the language big B. And so this is a cross product operation. Choose a string from A, choose a string from capital B, and then combine, put them together with a string from A first, and choose these strings in all possible ways, form all possible combined strings, and that's the language A concatenated with B. And finally, there's a kind of looping construct. This is pronounced A star, or it's called the Kleene iteration, or the Kleene closure. And A star is equal to the union for I greater than or equal to 0 of A to the ith power. And what's that mean? Well, A to the ith power is just A concatenated with itself I times. So this is A to the I. And note that because I can be equal to 0, one of the possibilities here is A to the 0, so A concatenated with itself 0 times. And what is that? Well, that's the language epsilon. So that's the language containing the empty string. So the empty string is always an element of A star. To summarize the last couple of slides, the regular expressions over some alphabet sigma are the smallest set of expressions that include the following. So let's define it. So the regular expressions are equal to epsilon is always a regular expression. Or another possibility is the single character C, where C is an element of our alphabet. Okay, so this is important. The regular expressions are defined with respect to some alphabet. So we have to pick a family of characters that will form the base cases of the regular expression. And here, we have one base regular expression for each character in the alphabet. And then we have the compound expressions. So another possibility is that a regular expression is the union of two regular expressions. Another one is that it's the concatenation of two regular expressions. And the last one is that it could be the iteration of a regular expression. So these 5 cases are the set of regular expressions over a given alphabet. Now, this syntax here for describing the regular expressions with these vertical bars and these different cases on the right-hand side in this recursive definition of R, if you haven't seen this before, this is called a grammar. And that's not important for this lecture. It's not what this lecture is about, but we'll be talking about grammars when we get to parsing. Next, I'd like to do a few examples of actually building regular languages, writing them out and thinking about what they mean. And as we said, whenever we're talking about a regular language, we first have to say what the alphabet is. And so for these examples, let's just use the alphabet 0 and 1. So these are going to be languages which consist of strings of zeros and ones. And let's start with a very simple example. Let's think about the language 1 star and what language that denotes. So, well, we know the definition of star. If we remember, that was the union over I greater than or equal to 0 of 1 to the I. Okay? And what is that equal to? Well, that's just 1 repeated I times. That's what the concatenation of 1 to the I means. Okay? It means 1 concatenated with itself I times. And so this is going to be the empty string. That's 1 concatenated with itself 0 times, followed by 1, followed by 1, 1, followed by 1 concatenated with itself 3 times, followed by 1 concatenated with itself 4 times, followed by 1 concatenated with itself any number of times. Okay, and so we can see that this is just equal to all strings of ones. All right, now let's do a second example. Let's think about the language 1 plus 0 concatenated with the language 1. Okay, and remember how concatenation works. It's a cross product, so we take every string in the first expression and combine it with every string in the second expression. So this is going to be equal to the strings A, B, where A is drawn from 1 plus 0, and B is drawn from 1. All right, and what can that be? Well, there's two choices for A. A could be 1 or 0, and B could be 1. So in fact, this is equal to the set 1, 1, and the strings 1, 1, the set containing the strings 1, 1, and 1, 0. All right? Let's do another example. Well, it's slightly more complex. Let's build up here to having 2 iterations in a union. So we'll have 0 star plus 1 star. And think about what that's equal to. Well, we already know what 1 star is equal to. That's equal to all strings of 1s. And so by analogy, 0 star must be all strings of zeros. And then we take the union of those two things. So this is actually really easy to write out. Let's write them out in this notation. So we have 0 to the I for I greater than or equal to 0. Okay, so that's 0 star union with 1 to the I for I greater than or equal to 0. That's the strings of all 1. So there's the set that this expression denotes. And for our last example, let's think about 0 plus 1 now, that iterated. Okay, so we put the star around the union of the two individual characters instead of having the star on each character individually and taking the union of the two things. So what is this expression equal to? Well, let's work with the definition of star. So we know that this is the union over I greater than or equal to 0 of 0 plus 1 to the I. And what does that look like? Well, that looks like, first of all, there's the empty string, right? And then another string in this language is drawn from 0 plus 1. And sorry, I shouldn't say another string, but another set of strings is from the language 0 plus 1, and then 0 plus 1 concatenated with itself, okay? And in general, it's going to be 0 plus 1 concatenated with itself I times. Okay, well, what does that mean? That means that at every position, if we have a string of length I, at every position we can pick a 0 or a 1 to plug in. And this works for any length string. This is going to be true of strings of every length. And so in fact, this language is just going to be all strings of zeros and ones. And in fact, what that means is it's the set, if we look back at our alphabet only consists of 0 and 1. And so this is the set of all strings that you can form over the entire alphabet. And that has a special name. When that happens, when you have a regular expression that denotes the set of all strings you can form out of the alphabet, we write that as sigma star. Okay, so just meaning all the strings of the alphabet iterated as many times as you like. One last point I want to make on this before we go on here is that there are actually lots of ways to write each of these different languages. There's not a unique way to write these. So for example, let's just take this language here, the second one that we did, and let me switch colors. Another alternative way to write this, since we know the meaning of it is these two strings, 1, 1, and 1, 0, is I could have written it as 1, 1 plus 1, 0. And that would mean exactly the same thing. These two expressions denote exactly the same set. Similarly with 1 star, I could write this as 1 star plus 1. Because this wouldn't change anything. Adding in the single string 1 wouldn't change anything since 1 is already included in 1 star. This might be kind of a silly way to write that set, but it doesn't matter. It has a meaning, and it means exactly the same thing as 1 star. And the point, again, is that there's more than one way to write down the same set. You can write multiple regular expressions that denote the same set.